What I'd like to do in this video is show you a relatively elementary derivation of the normal, or the Gaussian distribution. Now this class of functions, the Gaussians, is of central importance in mathematics. It shows up in many different branches, most famously statistics, where these functions are used to model a random variable, or describe data which seems to be centrally clustered around some value, the mean, and it seems to become less frequent as you move away from the mean. These Gaussians also show up in differential equations, such as when you're using a differential equation to model the diffusion of heat or molecular diffusion. But what I'd like to do here is show you a relatively clean and elementary derivation of this class of functions. We're going to begin our derivation with a thought experiment. Let's imagine you have the 2D Cartesian coordinate system, x and y here, and the origin is going to represent the center of a dartboard, the bullseye. So you're going to place the bullseye right at the origin there. And what you're going to do is imagine throwing darts at that bullseye. You're trying to aim for that bullseye. And you throw many, many darts, and you record the individual positions of the darts by these individual dots that I've drawn in here. Now, unless you're some expert at playing darts, what you'll probably notice is that almost none of these darts are going to actually land right at the bullseye. But what you should notice, as you throw, let's say, 1,000,000 darts, is that the positions of these darts are going to be centrally located. They're going to seem to cluster near the center. So most of the darts are going to land on the dartboard, hopefully, and relatively close to the bullseye. And as you move further away radially from the bullseye, there should be fewer and fewer darts. Our job now is to come up with a function that describes the relative probability of finding darts at particular locations on this dartboard. Now, the way we're going to do that is by defining what's called a probability density function, which I'm going to call phi. So this function phi here is going to take in a point on this 2D dartboard and give me the relative probability of finding a dart near that point. So the way to actually calculate a probability of finding a dart, let's say in a very, very small box. So the probability of finding a dart within this very small box, which I'm going to call dA, this infinitesimal area, is going to be the coordinate describing that box plugged in to this probability density function phi times the actual area itself, dA. There are some features of this function phi that we can intuit immediately. A couple of those would be that if we input coordinates which are relatively close to the origin, relatively close to the bullseye, we should get relatively high values for phi. And as we input coordinates which are further away from the bullseye, we should get lower values for phi, because we're most likely to find a dart near the bullseye, as opposed to way off. Another higher level feature of this function phi should be that if you integrate over all x and all y from minus infinity to infinity, you should get 1. And why is that? Because the probability of finding a dart anywhere on this 2D dartboard should be 1. There's another feature of this probability density function phi that we're going to assume, and it's going to be absolutely essential for continuing our derivation. And it's this, that this probability density function phi only cares about the distance away from the origin, the distance away from the bullseye, and not upon the angle made with the x-axis. Let me put that another way. Let's go back to this box, dA. This has a certain distance away from the origin. Let's call it r. It also makes a certain angle with the x-axis called theta. Imagine rotating that box, but keeping the area preserved. Let's rotate it over there to form dA prime. The distance away from the origin is of course the same. It's also r. The angle changes, but what we're saying of this probability density function phi is that if we plug in the coordinate describing that box, that first dA, into phi, we should get the same value as plugging in this coordinate describing the second box, the rotated box, into phi. What we're really saying about this function phi is that it's rotationally symmetric or radially symmetric. That is, this probability phi times dA is equal to phi of r only times dA, as opposed to writing something like phi of r theta. It has no dependence upon theta, only upon the radius r, the distance away from the origin. We've been talking about polar coordinates, about r's and thetas, but let's also recognize that each one of these boxes that we've been thinking of has an x coordinate and a y coordinate in Cartesian. And the next assumption we're going to make in our derivation is going to be this, that the x and y directions are statistically independent. That is to say, in terms of finding darts at particular spaces on the dartboard, the x-coordinate tells you absolutely nothing about the y-coordinate, and vice versa. The y-coordinate tells you nothing about the x-coordinate. What that statistical independence between x and y coordinates allows us to do is express this probability of phi times dA in another way. What it allows us to do is say that the probability of finding darts within this box is the following. F of x, where f is some new probability density function, taking in the x-coordinate times, and times because we're utilizing the independence between x and y, times f taking in the y-coordinate times dA. Again, we're saying that the probability here on the right-hand side is the product of f of x times f of y because of the statistical independence between x and y directions. And it's going to be the same probability density function, f, operating upon both coordinates, x and y, because there's no special distinction between x and y. Next, what I'll do is cancel out the dAs here and reveal the equality between these probability densities, phi of r and f of x times f of y. And the next thing I'll do is recall that in polar coordinates, the relation between polar and Cartesian is that r is equal to the square root of x squared plus y squared. And again, that's equal to f of x times f of y. It seems like here we're building up too many unknowns, too many variables, and too many unknown functions, phi and f. But there's actually a precise relation between those two functions, phi and f, and I'll reveal that relation in the following way. Now, let's set y equal to 0. If this statement is true in general, it must be true in a specific case, namely where y is equal to 0. Now, when you plug in y is equal to 0 there, you get the square root of x squared, which is just x. So on the left-hand side, I have phi of x. And on the right-hand side, I plug in y equals 0 there. And what I get, I'll commute there. So I get f of 0 times f of x. Now, this thing here, f of 0, is just some constant, some unknown constant. I'm going to just give that the name lambda for now. So lambda, the unknown constant, is equal to f of 0. What I discover here is that phi of x is equal to lambda times f of x, which is to say that phi, the function phi operating on any particular input, is but a scalar multiple lambda of f operating upon that same input. That is to say, phi is just some scalar multiple of f, namely lambda. With that knowledge that phi is a scalar multiple of f, I'm going to return up to this line here, where I have phi of the square root of x squared plus y squared as the input. So this input looks complex, but it's just one thing, it's one object, the square root of x squared plus y squared, being inputted into phi. Now, because phi is a scalar multiple, namely lambda of f, I set this equal to lambda times f operating on that very same input, square root of x squared plus y squared. So the equality between this, lambda times f of the square root of x squared plus y squared, is equal to f of x times f of y, is the key functional equation that I'm going to work with next. So you can see the result of that is that we've expunged this function phi, and we're now going to concern ourselves with the function f only. And the function f is actually going to be the function I'm interested in this video. Now, f is the function that I really care about in this functional equation, but I'm going to make a little modification just to make the solutions of the functional equation more apparent. And what I'm going to do is divide both sides by lambda squared. Instead of writing lambda squared here, I'm just going to write lambda times lambda. And what I have is that f of x divided by lambda times f of y divided by lambda is equal to f the square root of x squared plus y squared divided by lambda. And what you can see here is that I have f of some particular input, x, y, or the square root of x squared plus y squared, input it into f, and then divide by lambda. So what I'm going to do is define a new function called g of x, which is going to be whatever f of x is divided by lambda. And what that definition allows me to do is say that g of x times g of y is equal to g of the square root of x squared plus y squared. Now f is really the function that I'm interested in this video, but to find f, what I'm going to do is find g first. And g and f are just related by a scalar multiple, so once I find g, I know what f is immediately. So our goal now is to find functions g which have this property, that if I have two particular inputs, x and y, that if I take g of x multiplied by g of y, that's equal to g of a different input, square root of x squared plus y squared. So it's not immediately obvious which sorts of functions g should have this particular property, but we're actually going to solve this functional equation just by inspection. And to help us solve it by inspection, I'd like to consider a different functional equation, an easier one, just to give us a clue as to what sorts of functions are going to solve this equation. Let's say I have some function h that has the property h of x times h of y is equal to h of x plus y. So what sorts of functions have this particular property? That the product of two outputs is the same as the output of the sum of those two inputs, x and y. And if you reflect upon that a little while, perhaps this will remind you of the exponential function. That is, if I take e to the x, if I interpret exponentiation as that function h, e to the x times e to the y is equal to e to the x plus y. So this function, exponentiation with a base e, is one particular function h which will solve this functional equation. Of course, I didn't have to choose that particular base e. I could have chosen 5 to the x. I could have chosen this as a function, 5 to the x, because 5 to the x times 5 to the y is also equal to 5 to the x plus y. So we can immediately see the sorts of functions which are going to solve this functional equation, which have this property h of x times h of y is equal to h of x plus y. And those sorts of functions are going to be exponential functions. Now, I didn't pick that particular simple example randomly. I picked it because this looks like it has this property at some point, that this property is going to come up at some point. We can see that these functions g in this functional equation cannot merely be exponentiation, because this functional equation is not identical to this functional equation. But it's at least suggested that exponentiation would show up at some point, because we have this sum of squares inside the square root. But the problem is the square root here. We've got to somehow get rid of the square root in order to get something like x squared plus y squared. So the key insight is this, that the function g is composed of two operations. First, we need some operation that's going to get rid of the square root on the right-hand side. And the operation that gets rid of the square root is squaring. So g is first going to be square the input. Let's see what happens when we square the input here. We square x, that goes to x squared. We square y there, that goes to y squared. We square the square root of x squared plus y squared. That goes to x squared plus y squared. Now notice, these two modified inputs, x squared plus y squared, you sum these two and you get precisely this, which is now similar to that exponentiation functional equation. So first, g is going to be squaring the input. Then, secondly, you exponentiate it. Because you exponentiate x squared, you get, for example, e to the x squared. You square y squared, you get e to the y squared. You exponentiate x squared plus y squared. you get e to the x squared plus y squared. Now notice the product of these two is indeed equal to this, which is that property that we have coming from the exponential functional equation. As we were noting over here, we could have chosen the base e for this exponentiation, but we noticed that any base would do. Therefore, in this step, and this step where we exponentiate the thing that comes before, we don't have to choose base e necessarily. There's a bit of ambiguity there. So right there, there's a bit of ambiguity. We could choose any base. We could have chosen, when we have x squared, we could have exponentiated to 2 to the x squared. But remember, no matter which base I choose, I can always change the base. That is, 2 to the x squared is equal to e to some appropriate constant, let me call it constant a, times x squared. Turns out a in this case would just be the natural log of 2, but always remember with exponentials I can change the base and just modify the argument here. Therefore, the most general source of solutions coming from this functional equation for g are going to be this. G operating on some input, let's say x, is going to be first squaring, then exponentiating to some base. But I'm going to choose that base to be e, because the base e is most natural, but e to some constant. That constant is coming from the ambiguity of choosing a base, e to the a times the squared input. So you see, I have x first being inputted, it gets squared, and then it gets exponentiated to some base. I choose the base e, and I say that the exponentiation is equal to e to some arbitrary constant a times x squared. Let me perform a little sanity check here just to make sure these functions g, e to the ax squared, where a is some constant, actually solve this functional equation. So we're going to actually check whether g of x times g of y is equal to g of the square root of x squared plus y squared. So g of x is just e to the a x squared. G of y is e to the a y squared. And that's got to be equal to e to the a, the square of the square root of x squared plus y squared, squared. The right-hand side is, of course, equal to, up there in the argument, a times x squared plus y squared. I'll distribute the a times x squared plus a times y squared. And then, notice the exponentiation allows me to break that sum apart into a product, e to the ax squared times e to the a y squared. And that's indeed equal to what we have here. So that looks good. These functions will do the job. And since I know what the g's are, remember we said before that if I know what g is, I know what f is just by this scalar multiple relation. So from this definition that we had from before, we see that f of x is just lambda. Remember, lambda is another unknown constant, so lambda times g of x. Therefore, if g of x is equal to e to the ax squared, those functions that I'm interested in, that class of functions, f has got to be equal to lambda times e to the ax squared. And that is the most general class of function that I'm interested in. That's really it for the conceptual work in this video. The rest is going to be merely cosmetic, and just for the sake of completion, I'd like to show you what these constants are going to have to be. I'd like to make a few modifications to these constants. The first is going to be that I'd like a to always be a negative number. The reason being is that if it's positive, then I get e to some always positive number. If you take that to infinity, this f function blows up to infinity, which is no good for talking about probabilities, because as you move toward infinity, you should get lower and lower probability densities. So what I'd like is that this constant a, if it's always negative, and the way I'm going to do that is just by redefining some other constants. I'm going to let a be equal to minus h squared. H is just some of the number, so h squared is always a positive number, and the negative of a positive is a negative. So I'm just going to redefine some constants there. So I have still lambda times e to the minus h squared times x squared. And that's still equal to f of x. Now, this is important because h is just some number, and lambda is some number too. So let's take a look at what these sorts of functions look like. Just pick a value for h and a value for lambda. So let's set x equal to 0 here on this graph, and we see that its maximum value is going to be lambda, right there. This function is also even, that is to say, f of minus x is equal to f of x. Therefore, it has symmetry over the vertical axis. So whatever's going on over here is going to happen over here too. We see that as we take x toward infinity, this goes to 0. So this function is going to look something like this, going to the right, and by symmetry to the left as well. So we now have this general class of bell-shaped functions. There's an additional constraint upon this class of functions that's very important for talking about probability, and it's that the total area under these bell curves from minus infinity to infinity has got to be equal to 1. And why do we want that? Because the probability of x taking on any particular value from minus infinity to infinity should be equal to 1. Using calculus, we say that the integral from minus infinity to infinity, total area under this curve, f of x dx, has got to be equal to 1. And what we'll see shortly is that this constraint is going to reduce the number of unknown constants. Here we have two unknowns, lambda and h. It's going to reduce the number of unknowns to one unknown. So we see that f has got to integrate to 1 from minus infinity to infinity. So I'll just plug in f here. So I have the integral from minus infinity to infinity of, I'm going to yank the constant out, lambda, times e to the minus h squared x squared dx has got to be equal to 1. And what I'm going to do here is a little u substitution. So I'm going to let u be equal to h times x. And we see that by this substitution, this argument up here, instead of minus h squared x squared, is going to become minus u squared. So that's why I made that substitution. Take the derivative, du is equal to h times dx. Therefore, dx is equal to du over h. I make that substitution here, so I have lambda over h, the integral from minus infinity to infinity, of e to the minus u squared du is equal to 1. Now, this integral here, the integral of minus infinity to infinity of e to the minus u squared du, this is a very famous integral. It's one you actually need multivariable calculus to do, so I won't bother doing it here. I'll just link you to a proof in a Wikipedia article. This integral is very famous. The integral is actually the square root of pi. So this integral is square root of pi. So I have lambda over h times the square root of pi is equal to 1. And what I'll do here is rearrange this to say that lambda times the square root of pi is equal to h. Let me square both sides to get h squared is equal to lambda squared times pi. So h squared is equal to pi lambda squared. Let me substitute h squared up there into the argument. So I now say that this normalization condition, that the total area has got to be 1, this changes my class of functions. It reduces it to the following class, making the substitution for h squared. Lambda times e to the minus pi lambda squared x squared. So you give me any particular value you want for lambda. Again, lambda is just some unknown constant. And I'm guaranteed that the integral of this function from minus infinity to infinity is 1, which is, as I said, important for probability. So from restricting that class of Gaussians from that normalization condition, we get the following class of functions. F of x is equal to lambda times e to the minus pi lambda squared x squared, where again, lambda is just some number. Now, instead of just saying some number, let's gain a little bit of intuition about what lambda is doing for this class of functions. Suppose we allow lambda to be 1. So the function we get is e to the minus pi times x squared. And let me plot that over here. So we see that when x is equal to 0, we get our maximum value of 1. And then the curve dies off to 0 on both sides, symmetrically. Now, suppose we let lambda be equal to 2. So that function is going to have to be 2 times e to the minus 4 pi x squared. So again, we have our maximum value when x equals 0 of 2. But how should I draw this in? Well, remember, no matter what lambda is going to be, the total area under this curve has got to be equal to 1. So I've got to draw this curve so that this value gets pulled up to 2, but this total area has to remain the same. So if you imagine this like a physical object, the volume, or the area, I should say, has got to be preserved as I stretch it in this direction. So if it's going to be stretched in that direction, it should contract in these directions. So I have my maximum value there, and I have a now more contracted version of this physical object, and this dies off to 0 in both directions. But you can see here that if this were describing some data, there's more of the data which is clustered closer to the central value, in which case it's 0 here. That is to say, there's less variance in that data, and I'll use that word immediately, the variance in the data. That is, if I increase the value of lambda, I get a decreased variance. Now in stats, the symbol for variance is sigma squared. And if you take the square root of sigma squared, you get sigma, which is its own thing, which is called the standard deviation. So you get a decreased variance, you also get a decrease in the standard deviation, or standard dev, which is sigma. So increase in lambda means a decrease in sigma. Therefore, a decrease in lambda should increase sigma. And the next step, actually the final step for this video, the final cosmetic step, is to actually find a formula for lambda in terms of sigma. And we're actually going to find that they're inversely proportional. That is, lambda is inversely proportional to sigma. Here's how we're going to find that relation between lambda and sigma. Now, in stats, the variance, sigma squared, if I'm given some probability density function, the variance is defined in the following way. The integral from minus infinity to infinity times the squared deviations from the mean. In this case, the mean is 0, so the squared deviations in x from the mean is just x squared. So x squared times f of x itself, which is just lambda times e to the minus pi lambda squared x squared dx. So I'm going to have to solve this integral in some way. First thing I'm going to do is a little bit of rearrange. I'm going to yank the lambda outside. So I get lambda times the integral from minus infinity to infinity. I have an x squared here, but instead of x squared, I'm going to write it as x times x. So I have x times x e to the minus pi lambda squared x squared dx. And the reason I did that is I'm going to set this up for integration by parts. What I'm going to do is I'm going to let u be equal to x. So here's my u, and this other stuff here is my dv. So dv is going to be x times e to the minus pi lambda squared x squared dx. Take the derivative, du is equal to dx. V, this is its own u substitution, or variable substitution. And what this is going to be is actually minus 1 over 2 pi lambda squared times e to the minus pi lambda squared x squared. Then use the formula for integration by parts. U times v first. So I get minus x over 2 pi lambda squared e to the minus pi lambda squared x squared, evaluated within its limits. And let's not forget we have a lambda multiplying out front. And then minus v du. I have a minus sign there, so this is actually going to be plus the integral from minus infinity to infinity. We have 1 over 2 pi lambda squared e to the minus pi lambda squared x squared and dx. And so let's take a look at this first term first. We evaluate from minus infinity to infinity. This term here is going to go to 0 quicker than this term. So this first term actually goes to 0 when you evaluate at the limits. So what I'm left here is simply lambda times the integral from minus infinity to infinity of 1 over 2 pi lambda squared times e to the minus pi lambda squared x squared. And let's not forget what this is all equal to. This is still sigma squared. And the last step is going to be this. So I have this integral here being set equal to sigma squared. What I'm going to do is, this is a constant over here, and the lambda is also constant. Let me just switch those two around. So this is equal to 1 over 2 pi lambda squared, the integral from minus infinity to infinity, lambda times e to the minus pi lambda squared x squared. That's still equal to sigma squared. Now why did I do that? Should be a dx there. Because this integral over here, remember we said no matter what lambda is, this integral already satisfies that normalization condition. That is, this whole thing integrates to 1. And that's equal to what we had up here. So that's why it integrates to 1. So what I get is sigma squared is equal to 1 over 2 pi lambda squared. And let me solve for lambda squared. Lambda squared is therefore 1 over sigma squared times 2 pi. And what that means, let me come back up here. Lambda itself is equal to 1 over sigma times the square root of 2 pi. And that's the relation right there between lambda and sigma. And as I said, you can see that lambda and sigma are inversely proportional. Let's make the final substitutions for lambda into our class of Gaussians. So what I have is f of x is equal to lambda, so I'll make that substitution. 1 over sigma times the square root of 2 pi. And then e, and let's see what's going on out there in the argument. So I have minus pi lambda squared. So I see from this, minus pi lambda squared is equal to 1 over 2 sigma squared. So what I have up there in the argument of the exponential is going to be minus x squared divided by 2 sigma squared. And this is the class of Gaussians, which has a mean of 0. This Gaussian is centered at 0, and a standard deviation of sigma. That is, if I were to just pick some value for the standard deviation, this bell curve would look like that. It would be centered at 0. And then we have, at this inflection point over here, we have sigma plus 1 standard deviation to the right. And by symmetry, we have 1 to the left as well, so that would be minus sigma. And you can go further to the right and to the left for 2 sigma, 3 sigma, and so on. But suppose you wanted to center this curve at some other value. Let's say the mean is mu instead of 0. So mu is just some other number. So let's draw this curve. It's going to be centered at the mean mu instead of 0. And then to the right, you have mu plus sigma. And then to the left, you have mu minus sigma. So how do you make that adjustment to this equation? Well, remember, if you want to shift a curve to the right by mu units, what you do is you consider not f of x, but you consider f of x minus mu. So that means if I wanted to say the most general class of Gaussians with a mean of mu and a standard deviation of sigma, that would be f of x is equal to 1 over sigma times the square root of 2 pi times e to the following minus x minus mu all squared over 2 sigma squared. So that's the most general. Those are the most general Gaussians with a mean of mu and a standard deviation of sigma. And once again, the integral of all of these, no matter what value you choose for mu or sigma, from minus infinity to infinity, has got to be 1. And that's all I have to say about Gaussians in this video. Hopefully you enjoyed this fresh look at deriving this class of functions. If you enjoyed the content, consider subscribing to the channel, leave some comments below, and I thank you for your attention, and take care.